Nowadays, we can see that there are a lot of pollution happen caused by plastic waste that can be seen on land and also in water. Do you know the process to eliminate these plastics are time-consuming, costly, and also can cause other pollution, such as air pollution? This is actually due to the combustion process that is required to degrade the plastic waste. Plastic that we used before are mostly derived from propylene, a simple chemical component of petroleum, which is hard to degrade. Hence, to overcome this problem, in 1926, there was a French researcher named Maurice Lemoine, who was the first to discover about bioplastics from his work with the bacterium Bacillus megatherium. So, what is bioplastic? Bioplastic is a biodegradable material that comes from renewable sources. Here, we will be discussing about bioplastic production from microalgae, Chlorella vulgaris, which is a type of freshwater green microalgae that has gained attention for its potential as a sustainable and renewable source as bioplastics. Plastics are a daily use. All things mostly made by plastics, not just plastic bags, even drink bottles, food containers are also made of plastics. Currently, the global market for bioengineered algal bioplastics is still in its early stage. Therefore, this bioplastic innovation is very suitable in the global market where we can still reduce pollution in the high demand of plastic use. The market for bioengineered algal bioplastics is primarily driven by the increasing awareness of environmental issues and the need for sustainable solutions. Consumers are becoming more conscious of the impact of their purchasing decisions and are actively seeking products with reduced environmental impact. This trend has led to a rise in demand for eco-friendly packing materials, driving the growth of the algal bioplastics market.
Before we learn further about bioplastics by Chlorella vulgaris, let us first get to know Chlorella vulgaris a bit more. I am Muhammad Farizul and I will tell you more about Chlorella vulgaris. Chlorella vulgaris are green microalgae. They are in the division of Chlorophyta, family of Chlorellaceae, and order of Chlorellales. They are called green microalgae because of their green color. This green color is due to the reason that they contain chloroplast, which give them green color pigmentation. They have spherical shapes and have sizes range from 1 to 10 microns. This photosynthetic green microalgae lives in small polytrophic inland water bodies. Chlorella vulgaris are autospores, which mean they reproduce asexually by mitosis. There are usually 4 daughter cells produced by one parental cell. These daughter cells will undergo the mitosis and maturation process inside the cell wall of parent cell. After the daughter cells mature, the cell wall of parent cell will rupture and all 4 daughter cells will be liberated. For nutrient acquisition, Chlorella vulgaris is autotroph, an acquired nutrient by photosynthesis. This is due to the reason that they contain both chlorophyll A and chlorophyll B. They only need carbon dioxide, water, sunlight, and small amount of minerals to reproduce. This photosynthesis process will produce glucose for Chlorella vulgaris. Glucose then will undergo complex biosynthesis to produce the final product of polyhydroxybutyrate or PHB polymer. PHB polymer is produced as carbon and energy reserve and stored in the cytoplasm. Polyhydroxybutyrate polymer is an important substance in the production of bioplastics. This is due to the reason that the rapid degradation of it in the natural environments.
Now, let me enlighten you about the remarkable features of bioengineered algal bioplastic, utilizing the extraordinary capabilities of Chlorella vulgaris species. This bioplastic possesses exceptional characteristics that surpass those conventional plastics. Firstly, a notable feature of this bioplastic is their flexibility. Algal bioplastic can be precisely engineered to exhibit varying degrees of flexibility, ranging from rigid to highly flexible, depending on the specific application requirements. Through careful genetic modification of algae, researchers can tailor the polymer composition, enabling them to adjust the ratio of monomers, manipulate the length, and branching the polymer chains, and even introduce specific chemical modification. This deliberate alteration significantly enhances the flexibility of the resulting bioplastics. Shifting our attention to the thermal stability. Algal bioplastic can be engineered to possess superior thermal resistance, enabling them to withstand different temperature conditions without deformation or melting. Achieving this involves applying surface treatments or coatings that enhance the barrier performance of the algal bioplastics, ensuring minimal diffusion or permeation. Additionally, algal bioplastic exhibit lower thermal conductivity compared to the traditional plastics, which means they are less prone to the rapid heat transfer. This characteristic contributes to the maintenance of their structural integrity even when exposed to the higher temperature, as the heat is not easily propagated through the material. Furthermore, algal bioplastic can be engineered to possess outstanding barrier properties, effectively impeding the transfer of gases or moisture. This achievement is a result of several factors. For instance, through the application of genetic engineering and advanced processing techniques, researchers can precisely control the degree of crystallinity within the bioplastic. Higher crystallinity leads to a more ordered and densely packed structure, which impedes the movement of molecules through the material, thereby significantly improving the barrier performance. The overall barrier effectiveness can be further enhanced by incorporating additional layers or employing laminated structures. These additional layers serve specific barrier functions, such as providing superior protection against oxygen or moisture, which is particularly crucial for safeguarding sensitive products. In addition, some bioengineered algal bioplastic exhibit impressive resistance to UV radiation. By formulating algal bioplastic with carefully selected additive or stabilizers, this additive boosts the material's capacity to absorb or scatter UV radiation, effectively preventing UV-induced degradation, including discoloration, embrittlement, or the loss of mechanical properties. Moreover, algal bioplastic can take advantage of the natural photoprotective pigments produced by certain algae species, such as carotenoids or flavonoids. By incorporating these algae or algae-derived compounds, these natural pigments can be seamlessly integrated into the materials, minimizing the harmful effects of UV exposure.
Bioengineered algal bioplastic, specifically those derived from Chlorella vulgaris, can have several positive impacts on humans. While the primary focus of bioplastic is often on their environmental benefits, they also offer advantages that directly affect human well-being.
Here are some key positive impacts. The first one is biocompatibility. Chlorella vulgaris bioplastic can be engineered to be biocompatible, meaning they are less likely to cause allergic reactions or adverse effects when in contact with human tissue. This is particularly important for medical applications such as implants, prosthetics, and drug delivery system where biocompatible materials are essentials. Second, reduce toxicity. Traditional plastics are often derived from fossil fuels and contain harmful additives that can leach into the environment and potentially impact human health. Bioengineered algal bioplastic offer a safer alternative by reducing or eliminating the use of toxic substances, making them less likely to cause harm if ingested or inhaled. Third, biodegradability. While this point does relate to the environment, it indirectly benefits human health. Chlorella vulgaris bioplastic can be designed to be biodegradable, meaning they can break down naturally over time. This reduces the accumulation of plastic waste in landfills and oceans, minimizing potential harm to human health from exposure to microplastic and other plastic-related pollutants. Fourth, potential for medical applications. Chlorella vulgaris bioplastic possess unique properties that make them suitable for various medical applications. Their flexibility, strength, and biocompatibility make them potential candidates for tissue engineering, wound dressing, and regenerative medicine. For example, they can be used as scaffolds for tissue growth or as carriers for targeted drug delivery, enhancing treatment effectiveness and patients' outcomes. Last one is improve food packaging safety. Bioplastics derived from Chlorella vulgaris can be used for food packaging, providing a safer alternative to traditional plastic packaging materials. By reducing the risk of chemical leaching and contamination, these bioplastics help maintain the quality and safety of food products, ensuring better consumer health and reducing the potential for exposure to harmful substances.
Compared to other species of algae such as spirulina, Chlorella vulgaris has a lot of potential in the market for the production of bioplastics since the quality of the products are greater. Even though Chlorella vulgaris are applicable in various industries, most of the bioplastic products from Chlorella vulgaris are still at their research level. The products are yet to be officially launched and commercialized in the market. For example, Chlorella has been used in the production of bioplastic films by the mixing of Chlorella vulgaris and polyvinyl alcohol or PVA. Since the production of bioplastic films still has its deficiency in their physical and chemical properties, they could not be commercialized yet. Thus, University of Indonesia has done a research to overcome the problems by looking for a great compatibilizer for the PPA Chlorella bioplastic films. However, the main point is, Chlorella vulgaris surely is in the spotlight of bioplastic production. As for the bioplastic films, the use of chlorella has helped in reducing the cost since microalgae do not need any prior treatment for plastic fabrication due to their small cell size. It also helps to overcome the thermoplastic properties problems of PPA other than helping the plastic to be degradable. In addition, a green technology startup called Algix has introduced Bloom, the first algae-blended EVA in the footwear industry. It serves as a sustainable component in flexible foams used in high-rebound items like athletic footwears. They make Bloom foam by extracting the biopolymers from the microalgae and supplying it to well-known brands like Adidas and Billabong.